This slide provides an introduction to the topic, RPC mobile phases, focusing on best practices and trends. This training is at an intermediate level, specifically tailored for pharmaceutical analysis. This slide outlines the agenda for the session. We'll cover RPC mobile phase selection and best practices, including mobile phase preparation techniques like premixing, filtration, and degassing. We'll also discuss balanced absorbance MPs, high pH MPs, when to use them, and strategies for avoiding ghost peaks, focusing on reagent quality and MP shelf life. Finally, we'll touch on other topics such as ion pairing reagents, Chaotropes, phosphoric acid, and MTBE as a THF replacement. This slide discusses mobile phase preparation, specifically manual premixing. It explains why premixing MP can be used for isocratic analysis and why pump mixing is generally preferred. It highlights that while measuring solvent volumes separately in a measuring cylinder is acceptable, volumetric flasks and pipettes are not recommended. Pump blending offers better convenience, and modern pumps provide good compositional accuracy, compensating for delta volume of mixing and compressibility. However, online degassing is mandatory. This slide also references a study by J.P. Foley et al. On volume change when mixing with water. This slide addresses the question of whether to filter mobile phases. It recommends MP filtration but notes that it may not always be necessary. It suggests filtering all aqueous buffers through 0.45 micrometer membrane filters, preferably nylon. It states that filtering HPLC grade solvents or purified water is generally unnecessary, as they are pre-filtered. Filtration may also be optional for high-purity buffers, such as ammonium formate at 99.995+% purity. The slide also refers to an article by M.W. Dong on common faux pas in HPLC. This slide covers degassing, specifically using a vacuum degasser. It emphasizes that online vacuum degassing is the norm for accurate pump blending. Vacuum degassers typically have small volume, semi-permeable Teflon tubes and an evacuated chamber. The vacuum pump should remain on continuously, and all 4 solvent lines should be filled with solvents to prevent the pump from sucking air. The slide references a chapter in HPLC and UHPLC for practicing scientists by M.W. Dong for more information. This slide discusses the use of balanced absorbance mobile phases for low UV detection to reduce gradient baseline shift with TFA or formic acid. This is achieved by reducing the additive content by 40% in MTBE. The slide presents 2 chromatograms illustrating the difference in baseline shift between using 0.1% TFA in both MPA and MTBE versus using 0.05% TFA in water, MPA, and 0.03% TFA in ACN, MTBE. Reducing the TFA concentration minimizes baseline shift, although it may result in broader peaks. The slide references Chapter 9 of HPLC and UHPLC for practicing scientists by M.W. Dong. This slide discusses the use of high pH mobile phases as an option for analyzing water-soluble basic drugs to increase RPC retention and improve peak shapes. It notes that prior to the 1990s, high pH mobile phases were not feasible due to the dissolution of silica-based columns at pH 8. Newer high pH compatible columns offer an attractive approach for separating water-soluble basic drugs like opioids, providing good retention, improved peak shape in RPC and MS compatibility. The slide references a study by M.W. Dong G. Miller and R. Paul on MS-compatible ICH impurity analysis using a high pH mobile phase. This slide highlights that high pH methods are useful for water-soluble basic drugs such as opioids. It shows a chromatogram using a Waters Xtera MSC18 column with a mobile phase of 20 mm ammonium bicarbonate pH 9.1 buffer, MPA, and ACN MPB. The gradient runs from 3 to 50% B in 40 minutes, then 50 to 80% B in 3 minutes, at a flow rate of 1 ml per minute at 50 degrees Celsius. Several peaks are labeled, including critical pairs and API peaks. The slide references a study by M.W. Dong G. Miller and R. Paul on MS-compatible ICH impurity analysis with a high pH mobile phase. This slide addresses ghost peaks in gradient analysis, a common problem. Case Study 1 shows that most ghost peaks are contaminants in MPA. The issue was resolved by rinsing mobile phase bottles with ACN/water instead of using them directly. Data from Eileen Zhao at Genentech in 2013 demonstrates that eliminating the ghost peaks can be achieved with proper rinsing. The slide recommends using high-purity reagents to prevent ghosting peaks and always checking gradient blanks. Okay, let's start with the shelf life of mobile phases. Determining the exact shelf life of a mobile phase isn't an exact science and can be quite tricky. For aqueous mobile phases, the shelf life is limited because of the potential for bacteria or algae growth, especially with ammonium buffers at a neutral pH. So, these are just some general estimates. Now let's talk about ion pairing reagents in reversed phase chromatography, or RPC. Ion pairing reagents are often used in older methods to increase retention. These reagents are detergent-like mobile phase additives that help retain acidic or basic analytes. However, these methods are generally less reproducible and not compatible with mass spectrometry or gradient elution. A common example is sodium hexyl sulfonate. A notable exception is the use of MS-compatible HFIP, hexafluoroisopropanol, in the separation of oligonucleotides, which is an emergent new drug modality. Let's move on to chaotropes in RPC. Chaotropic agents are polyvalent ions that can increase retention and selectivity of basic analytes by forming neutral ion pairs. They also improve peak tailing, which is beneficial for analyzing proteins, detergents, and antibiotics. Chaotropes are better suited for gradient analysis but are generally not MS-compatible. Now let's discuss phosphoric acid and methyl tert-butyl ether, or MTBE. 0.1% phosphoric acid is underutilized, even though it's transparent down to 200 nanometers and useful for purity methods of raw materials. Keep in mind that phosphoric acid is not MS-compatible. Tert-butyl ether, or MTBE, can be a substitute for THF in the mobile phase B. Although it has limited miscibility with water, it doesn't form peroxides.